Hi, this lesson is about the substitution rule for integration. It's sometimes called u-Substitution. So, with this rule, it allows you to evaluate integrals, both definite and indefinite integrals, where the integral isn't quite as straightforward as previous integrals that we've done. So, what the rule says is that if you have an integral f of g of x, which remember is a composite function, and the derivative of the inner function or some form of it is part of that integrand, then you can replace the g of x by u, and the du is actually your g prime of dx. So it's often the opposite of chain rule, which when we were taking derivatives, but not always. When you have a composite function, you you typically let u equal the inner function of the composite function, and then you take the differential of both sides of that equation. So let's look at the next several examples, and you'll see a wide variety of different ways that u-Substitution is used to evaluate integrals. So we start with an indefinite integral. We have the integral of 3x squared times the square root of x cubed plus 1 dx. So that's a product of two functions. The square root of x cubed plus 1 is the composite function. So we're going to let u equal the inner function of the composite. Then we take the differential of both sides. Remember, when you're taking differentials, you're taking the derivative, but instead of writing du dx, the du stays on the left and the dx stays on the right with the derivative. So although we're integrating, you're using derivatives within this rule. Then notice that u is the value that's right here, and my du is the rest of it, this and this, 3x squared dx. So we are substituting. So that's exactly what we're going to do. When we substitute, that means that you get the square root of u du. That's equivalent to the original function, but written in terms of u. Now, this is something easy to take the antiderivative of because it's u to the 1/2. So you add 1 to the exponent and multiply by the reciprocal, and we get 2/3 u to the 3/2 plus c, because it's indefinite. So don't forget the constant of integration. But u is equal to x cubed plus 1. So your integral value is 2/3 x cubed plus 1 to the 3/2 plus c. All right, so let's do another one that's similar in terms of your substitution, but there's going to be an extra step here. So again, this is a product of two functions. The composite is cosine of x to the 4th plus 2. The inner function is what we let u equal. That's the inside of the composite. Then the differential, if you take the derivative of both sides of u, you get du is 4x cubed dx. Now notice that I have a 4 here, but my original function does not have a 4, but I do have x cubed dx. So in order for us to be able to replace these two expressions, x cubed dx by du, that means you have to multiply both sides by a 4th. And what that will do is it will make this into just x cubed dx, which is exactly what you have in the original problem. So when you multiply both sides by a 4th, you get 1/4 du equals x cubed dx. And so 1/4 du replaces the dx and the x cubed in the original problem. So now we make our substitutions. We let u equal x to the 4th plus 2, and 1/4 du will replace the x cubed dx. So we end up with this integral. Now that's a straightforward integral to compute. The antiderivative of cosine is sine, so it's 1/4 sine of u plus c, and then in the end you replace u with what u is equal to, so your final answer is 1/4 sine of x to the 4th plus 2 plus c. So remember, with all of these problems, your answer, if you take the derivative of this, let's say this is f, and so if we take the derivative of this, it should equal the original function. And our original function was our integrand, right? So in order to find the derivative of 1/4 x to the fourth plus 2, you have to apply chain rule. So the derivative of sine is cosine of x to the fourth plus 2 times the derivative of the inside, which is 4x cubed, right? But remember, there's a 1/4 here, so there's a 1/4 here. So the 4's cancel, so it actually equals exactly what we started with. Cosine x to the fourth plus 2 times x cubed, which was the original problem. So until you get really comfortable with integration, I do suggest that you check your answers by taking the derivative of the integral and then of the answer you get with your integral and making sure it equals the original integrand. All right, so here's another one. We want to find the integral of tangent of x dx. So this one is not a composite function. So it would be kind of difficult to figure out what should I let u equal, but we can rewrite it in a different way. So let tangent equal sine over cosine. So we're integrating sine of x over cosine of x dx. So your u is either going to be cosine or sine. There's only one correct choice. So you need to choose u as your, you need to choose the denominator as your u. U is cosine of x, and therefore du is negative sine of x dx, but you have sine of x dx in your original problem. So in order to get rid of this negative here, multiply both sides by -1. So negative du is going to replace sine of x dx. So now we can make our substitution. So whenever you're substituting, your u can be in any position in the original function, but your du or any coefficient in front of du has to look exactly like what you see there. So sine of x dx is sine of x dx here, not in the denominator. All right, so now we make our substitution. And so I get the integral of negative du over u. That's the same as 1 over u, or negative 1 over u. The antiderivative of negative 1 over u is negative ln of u. Remember, we put the u in absolute values because the domain of your log function is only positive numbers, and we don't know what our limits are, plus c. Then you replace u with cosine, which is what we let it equal originally. So your answer or your integral value is negative ln absolute value of cosine of x plus c. All right, so here's several more. We want to integrate 6z squared ez to the third dz. So again, my composite function is the ez cubed, and the inner function of e to the z cubed is z cubed. And your du, when you take the derivative of both sides and leave the differentials, du on one side, dz on the other, is 3z squared dz. Now notice I have a 6, not a 3, so I need for it to look exactly the same. The du has to look exactly the same. So if you multiply both sides by 2, you get that 2 du equals 6z squared dz. So 2 du replaces 6z squared dz when you make your substitution, and u replaces z cubed. And that's what you see here. So I have 2 e to the u du. The antiderivative of e to the u is just itself. So your answer is 2 e to the u plus c. But then in the end, you replace u with what u is equal to. So we have 2 e to the z cubed plus c. All right, so let's do another one. I'm going to use colors here to help us see our substitutions. So we want to evaluate the integral from 0 to 4 of the square root of 2x plus 1 dx. So this one is a definite integral, which means we have to evaluate our limits. So I'm going to let u equal the inside part of the composite function, which is 2x plus 1. That's what you see here in the blue box, and that's what matches up with what you see here inside of the radical. And then your differential du is 2 dx. But notice I don't have a 2 as a coefficient in the original problem. All I have is a dx. So the way you get rid of that 2 is that you multiply both sides by a half. So I have 1/2 du equals dx. So 1/2 du will replace this, will substitute. So that's what we do here on the right. We make our substitutions. So I have the integral of 1/2 square root of u du, which is the same as 1/2 the integral of u to the 1/2. And then we can take anti-power rule and apply it, which gives us this line here, 1/2 times 2/3 u to the 3/2. And notice that I haven't written my limits because my limits don't make sense in terms of u, and I haven't reevaluated them. So if I go back to using my limits for x, I now have to replace my u with 2x plus 1 and then evaluate my limits of 0 and 4. So now I can apply the fundamental theorem of calculus, plug in the upper limit, and then plug in the lower limit and subtract. So that's what you see here. So that gives us 1/3 times the square root of 9 to the 3rd power minus the square root of 1 to the 3rd power. Then the 1/3 comes down, and then the square root of 9 to the 3rd power. Well, the square root of 9 is 3. When you cube it, you get 27, and 1 to any power is just 1. So you have 1/3 times 26, so your answer is 26/3. Okay, here's another definite integral. I want to integrate from pi over 4 to pi over 2 of cosine cubed of x times sine of x dx. So here I have a product, and my composite is cosine cubed of x. The inner function is cosine. So the orange box indicates my u, which is what you see above in the integral, underlined in orange. So when I take my differential on both sides, you get that du is negative sine of x dx. But I don't have a negative sine of x dx. I have sine of x dx, which is what you see here. So the way to get rid of the negative is to multiply both sides by -1. So negative du will substitute in for sine of x dx. Now, this time I'm going to change my limits in terms of u so that I don't have to substitute back later. And that's what I'm doing right here. So when x is pi over 4, remember that's your lower bound, your u is the cosine of pi over 4, which is root 2 over 2. So that's what you put here in your limit. And when x is pi over 2, that was the upper limit, your u is a cosine of pi over 2, which is 0. Okay, so we have our limits. There's a 0. And then we replace cosine cubed of x by u cubed, and sine of x dx becomes negative du. So this is what we are integrating. So now we do anti-power rule. We have negative 1/4 u to the 4th, evaluated from root 2 over 2 to 0. And then you just plug in your limits. Remember, you don't have to go back and substitute in for u because we reevaluated the limit values in terms of u. So you plug in 0 first, then you subtract and you put in your lower limit. Notice that my lower limits are kind of different than what we're used to. The bottom limit is bigger than the upper limit, but that's okay as long as you are consistent with what your substitutions were here when we did that work on the right. Okay, so when you work that out, you get negative 1/4 times negative 4 over 16. Two negatives make a positive, the 4's cancel, so your answer is just 1/16. Okay, so here's another one. We want to integrate from 0 to pi over 6 of secant to the 4th of theta d theta. So this one doesn't stand out as something that I recognize, but I can do a little bit of substitution and some work here to help us see something that might look familiar. I know that I can rewrite secant to the 4th as secant squared of theta times secant squared of theta. Now, that's somewhat helpful because I know that secant squared is the derivative of tangent, but I can't do anything with the integral as it is, secant squared and secant squared. So I'm going to make a substitution. Secant squared is equal to 1 plus tangent squared of theta. That's one of the Pythagorean identities. Once I write it like that, my integral is a product of two expressions, and one has the u in it, and one has the du. So a good choice is to make u equal to tangent, because then my differential du is secant squared d theta. So I have it here in the orange box because that matches up with what I underlined in orange in my integral right here. And then here I reevaluated my limits. When theta is 0, tangent of theta is also 0, so that's my lower limit. And when theta is pi over 6, tangent of pi over 6 is 1 over root 3, so that's my upper limit. So that way I don't have to worry about substituting back in for u, so I can just go ahead and integrate. So it's easy to integrate 1 plus u squared. Remember, with u-substitution, you should always be integrating something that looks simpler or easier than what you started with. It shouldn't be getting more complex. It should be getting more straightforward. So here we've integrated, so it's u plus 1/3 u to the third. Now we plug in our limits. So you plug in your upper limit first, minus your lower limit, and don't forget you have to distribute that minus according to the fundamental theorem of calculus across. So I put parentheses there. So you end up with 1 over root 3 plus 1/3 times 1 over 3 root 3. And when you multiply the second fraction, you have 1 over root 3 plus 1 over 9 root 3. So our common denominator is 9 root 3. And when you multiply the first one by 9, you are able to combine and get 10 over 9 root 3. And if you were to rationalize it by multiplying top and bottom by root 3, you end up with 10 root 3 over 27. Okay, here's another one, example 8. We want to evaluate the integral from 1 to e of ln of t over t dt. So this time I have a quotient. There is no composite function here, so you really have to try to figure out which one is u and which one is du. So sometimes without experience, you might have to try more than one option. But if you let u equal ln of t, then your du just naturally works out to be 1 over t dt. That's exactly what you see here. Remember, your du has to be exactly what you see in the original function. The only thing it could be off by is a constant or a coefficient, which you can easily manipulate on both sides. So then here on the right, I reevaluated my limits. So when t is 1, ln of 1 is 0. When t is e, ln of e is 1. So my new integral is the integral from 0 to 1 of u du, which is 1/2 squared. When you take the antiderivative, plug in 1 and 0, and your answer is just 1/2. Okay, here's another one. We want to evaluate the integral from 1 to 2 of e to the 1 over x squared. So this one is a very traditional u-substitution problem where I have a composite function in the numerator and then another function in the denominator. The inner function of e to the 1 over x is 1 over x. So that's your u. So remember, 1 over x can be written as x to the negative 1. So when you take du, you get that du is negative x to the negative 2. Now, x to the negative 2, if you were to rewrite it, becomes negative 1 over x squared. Now, I have 1 over x squared here, but I don't have the negative. So multiply both sides by negative 1. That means that negative du will replace what I circled in the original problem. On the right, I reevaluated the limits. When x is 1, u is 1. When x is 2, u is 1/4. So 1 over 2 squared, which is a fourth. So here is where you see all of the substitutions. My limits go from 1 to 1/4. My substitutions for the integrand are negative e to the u du. Now the antiderivative of e to the u is itself, so you get negative e to the u evaluated from 1 to 1/4. Always plug in the upper limit first, minus the lower limit. So you get negative outside of e to the 1/4 minus e to the first. And if you were to distribute the negative sign, you would get what you see here. E to the first just becomes positive e, and then minus e to the 1/4 becomes the fourth minus the fourth root of e. Okay, so let's move on to another one. So we want to evaluate the integral from 2 to 3 of x squared over x minus 1 dx. This is another one which might not be so straightforward, but I've mentioned this scenario before in previous lessons where I have a degree on top that is bigger than the degree on the bottom, and sometimes you need to use long division in order to simplify this into a different expression that you can take the antiderivative of. Even if you tried using u-substitution in the original problem, it really wouldn't work out. If you let u equal x squared, your du is 2x dx. There's no way to make a replacement for 2x dx. You don't have an x dx anywhere in that problem without rewriting your x squared, and so that really wouldn't help. And if you let u equal x minus 1, well, then your du is just dx, and then what do you do about the x squared? So you can't use u-substitution immediately, but we will after I apply long division. So this is where the long division is happening. So I have x squared being divided by x minus 1. So x squared divided by x is x, so that's your quotient right here. And then you multiply x across your divisor, which gives you the second line of your long division problem, which is right here. Then you subtract that line from the top line, and you get a remainder of x. So the way you rewrite your integral is that it is the integral. So this integral is equivalent to this one right here. So it's the integral from 2 to 3 of x, which is my quotient, plus my remainder, which is x over x minus 1. All right, so the x is easy to deal with. We know how to take the antiderivative of this term, but the second term, x over x minus 1, that's where u-substitution is going to be helpful. I'm going to let u equal my denominator. So that's what you see here. If u is equal to x minus 1, then du is dx. Well, that's fine, but I have an x here. So what do I let x equal? Because I need to replace everything with some format of u. So if you take what u is equal to, it's equal to x minus 1, and solve for x, that means x is equal to u plus 1. So that's what you see here. I have u plus 1 replacing the numerator x, and x minus 1 getting replaced by u. Okay, I also need to reevaluate my limits for the second part of this integral, which you see below. So my limits are 2 and 3. So when x is 2, u is 1, and when x is 3, u is 2. So I have two things going on here. I have my first integral, which was easy to do. I can take the antiderivative of x and then plug in the 3 and the 2. But here I needed to use u-substitution. But before I can actually integrate this, because again, we don't really have a rule to integrate that, we have to do a little bit of algebra, which is to divide each term by u. So u over u is 1, and 1 over u is 1 over u. So we are integrating this here, the integral from 2 to 3 of x dx, plus the integral from 1 to 2, remember that came from here, new limits, because they're in terms of u, of 1 plus 1 over u. Now the rest is very straightforward. So the first one is just anti-parallel. We have 1/2 x squared, evaluated from 2 to 3. And in the second integral, the antiderivative of 1 is u. The antiderivative of 1 over u is ln of u, evaluated from 1 to 2. Then you do the arithmetic, plug in the numbers according to the fundamental theorem of calculus, which is what you get on this line. Combine all numbers possible, and you end up with your final answer found here below of 7/2 plus ln of 2. So that was a nice diversity of problems that you just saw. So now you should try the homework. Good luck.